So let's just do this again. And like I said before, if you've got questions, just pop them down as I go. But now that you're actually hearing the material, it might actually make sense. Okay, so what's a supernova? What's a stripped envelope supernova? We will start with that. First of all, well, a supernova is a type of explosion, a stellar explosion, when a massive star that's born with at least 8 to 9 times the mass of the sun, usually way more than that, reaches the end of its life. So when it reaches the end of its life, it runs out of fuel completely in the center, it collapses, and it explodes, right? Now, different types of supernovae for different types of stars. If your star is born, if your star, when it dies, has still a lot of hydrogen in its envelope, as I hope you can see, it looks like it works, then you have what we call type 2 supernova. If you've got no hydrogen but a whole bunch of helium left, then you've got 1b. If you have no hydrogen and no helium, then you've got a 1c. These type 1c supernovae are some of the rarest, but they also require some of the most weirdest environments to happen because you need to strip all of the hydrogen and all of the helium. Second time presentations are always the best, that's right. So you need to strip all of that hydrogen and all of that helium from the star in order to get that type of supernova. So this is what we have with this particular paper. So 2018 IJP is type 1c, broad line actually type 1c, but we're not going to fuss with the details. Supernova, but what's very special about it is that it has a hydrogen-rich shell around it. Now, where could that come from? We'll get back to it at the end, but I'll mention it now. So, of course, when your star loses the mass, loses all of that material, it goes somewhere, it goes into space, right? So if you can see this picture, and I think you can, this is an example of this is kind of a bow sort of shell, but it will be in a shell. It's just that this side is illuminated or something. That's been lost by a star. Eta Carinae is a specific type of star. It's called a luminous blue variable that loses a tremendous amount of mass, because the envelope just explodes. Just simple, just goes boom. Not boom enough to make a supernova. It doesn't disrupt the entire star, but it makes it lose a tremendous amount of mass, like 10 times the mass of the sun, sort of tremendous amount of mass. So there are possibilities. There's more than that I'll mention at the end. But all of that stuff gives you what we call circumstellar medium, CSM. So circumstellar just means around the star. It comes from a couple of Latin words. And medium just means stuff. So it will be gas mostly, dust, a whole bunch of stuff like that. So what does that mean for our supernova? Well, first of all, how did they find that CSM? What traces of CSM do we have? Well, I think you can see the paper there. Let's start with the light curve. I started with the spectrum in my first presentation that didn't have sound. We'll start with a light curve. So a light curve is one of the first plots that we make for a supernova, and it's very simple. You just plot the luminosity against the time after explosion. So in this case, the explosion occurred around here, and then we recorded the brightness. Now, this is weird, which I know to the untrained eye might not look weird, so let me show you what it should look like. For a supernova of that type, it should look like this. It should have a nice peak and then some nice linear decay from radioactive decay. That's why it looks linear. But that's not what it looks like, does it? It looks really freaking weird. It has this first peak, which we expect, and then it has another peak again. It actually has a couple of wobbly-weebly lines right there, two minor peaks. Where can that come from? This is from the interaction with the circumstellar medium. It's kind of similar to the idea of well, not really, because they don't interact, but recombination is the word for it. It's when your material is ionized, and so the nucleus and the electrons are separated, and then when the gas cools, then the electrons come back, and when they come back onto the atom, they launch a photon, which we can see. So these extra photons make extra light, and make the light curve deviate from that linear shape. So that's what happens in type 2 supernovae, type 2p supernovae. That's what's going on here, right? So this is a first indication that around 24 days, there is an interaction with a circumstellar medium. 24 days is not a lot of days, right? It means that stuff was really, really close, which is freaking weird, okay? And also it's made of hydrogen. So where's the helium? Many questions. I have many questions, very few answers, because, you know, it's the forefront of science. That's where you ask all of the questions, and it takes years to answer them. Now, the light curve is not the only place where you have this weird stuff, this weird interaction. You also see it in the spectrum. Let me check if everyone is, yes, everyone can see it. So this is a spectrum. It's basically a rainbow. It's very simple, right? So you've got the red here, we've got the blue here, and it's a bunch of squiggly lines. I know it looks like a bunch of squiggly lines. I was there, you know, when I was a young PhD student, and people would be like, oh yes, this makes perfect sense. Of course, this is this line, this is this type of supernovae. So let me just walk you through it. We're going to only care about the vertical line, okay? Everything else is either noise or broad lines from the supernova, but what we care about is this vertical line, because that's the interaction with the circumstellar medium. That's the supernova going through that dense cloud of gas and stuff and interacting with it. Now, what's really interesting is the location of that vertical line, right? Because that vertical line is at this sort of wavelength, which corresponds to hydrogen, right? If it was somewhere else, like around here, then it would be helium. And the fact that it's hydrogen, like I said, is pretty freaking weird, because where's the helium? And how did it lose all of that? Because it had to be that type of supernova, right? The type 1c, it had to lose the hydrogen and the helium. But the hydrogen is still there. And is it the same hydrogen? Is it the same star? Is it a binary companion? Is it something nearby? What's going on? Many questions. One of the that reminds me of a quote by, I can't remember who. That's like, "Eureka is not the best word to hear in science. The best word to hear in science is that's weird," because that's where good discoveries come from. Now, this supernova is really freaking weird, like I said. But it's not the first time we've seen one like that. So supernova 1997 CY is pretty close, they say. So it's been 20 years since we found one like that. So it's not surprising that they don't have a tremendously good idea of where it's come from. So what their explanation of how it happened is pretty generic, which I don't blame them for. It's not the point of the paper. The point of the paper was to explain what was going on and give the observations. Then trying to model that type of supernova is someone else's job. That's just the way that science goes. So what they say is that this could be produced by a previous evolutionary stage, which means Wolf-Rayet star, red supergiant, luminous blue variable. So the Wolf-Rayet star, let me just explain, is a massive star that's got a very strong wind, and it's so bright, basically, that the photons are pushing stuff outwards into space. Crazy. Red supergiants, they're like Betelgeuse, right? So they're very bloated, they're very massive, so their outside is really cool, and they've got these weird pulsations. And so these pulsations can push the outside of the supernova, the star, far enough out that then it's unbound from the star and it cools down and makes dust and it releases that stuff into space. That's exactly what happened to Betelgeuse, by the way. That's why it faded, because it made dust in that sort of way. What else? And luminous blue variable is like Eta Carina. Like I said, something explodes in the envelope. So that's it. That's what we've got for that weird stripped envelope supernova. Loads of possibilities, loads of questions, and some very exciting science to come. So thank you very much for bearing with me. I think the sound worked this time. Oh God, it pisses me off. Every time I stream, there is a different problem. I'm learning so much, but it's just so annoying. I just want to do science, not fuck around with computers that don't work and streaming services that only half do their jobs. So let me check if there are questions rather. Would it be so Lycos asked, would it be considered common as there is evidence of another star that has similar data? I wouldn't consider it common at all. We see a lot of supernovae these days. I think last year we discovered 25,000 in the year. We've got entire telescopes and surveys dedicated to them. Actually, I'm going to stop sharing because there's no need. So no, 2 in 20 years, I wouldn't say. Well, it's not common, and that's why it's so interesting. And that means that it would be a pretty rare sort of mechanism, right? The fact that we don't see them a lot. Samwaf asks, what is the dust? That's a very good question. Stardust is weird dust. It's not the dust that you get in your office. The dust you get in your office is mostly your skin that's peeled off and stuff like that. The dust in stars is basically, so when things cool down, your gas turns into, you can get molecules in your gas, and then some of these molecules, often titanium oxide, it's just metals that aggregate together. Then they can start like accumulating with each other, and so they're not very big dust grains, right? They're much smaller than what you get in your office. You can't see them. You wouldn't be able to see them with your eyes, but because it's like many molecules big, then it's no longer just a gas. It's just it's starting to turn into a solid, basically. Do these events occur in binary stars only? That's a very good question, Tommy. No, they wouldn't just occur in binary stars. Binary stars would help because you can, well, they could help give you that CSM because you can strip another star with gravity, basically. And so that would help a lot because, like I said, where does the hydrogen come from and why is there no helium? Because if you lose your hydrogen, you must lose your helium to give the type of supernova you have. But if you have that type of stripped star and then next to it, you've got a hydrogen-rich star that's being stripped by the nearby very dense star that's about to die, then you can get that sort of CSM maybe. And that could be a way to go around all of the weirdness. Thanks, Lycos, for being sympathetic to my troubles. Sam asks, the dust appears after the explosion. Okay, so that's a very interesting question about stellar dust and dust and supernovae in general. So the dust from the star appears before the explosion as supernova. When the material goes out into space and starts to cool down, it will then, stop being ionized, turn into molecules and condense and potentially make dust. That's what happens with things like Betelgeuse, for example. In supernovae, you can get dust as well after they've exploded, and it doesn't actually take that long to make the dust, as we've seen with 1987A, which exploded in 1987. Lycos asked, how dense was the star before it went supernovae? Dense, I can't, I don't know on top of my head the kind of density that, so I'll give you a vague enough answer. I can't give you a number because I don't have it on top of my head, but a star like this was actually pretty dense. It was like a stellar core, whereas something like a red supergiant, well, it depends. If it was a Wolf-Rayet star, it would have been pretty small and pretty dense. If it was like a red supergiant, then the outer layers are actually very fluffy. And when you see, that's the interesting thing with red supergiants, because when you see them represented in the media, they're just like a big red circle, but that's not what they would look like if you could see them like that, because their outer layers are so fluffy and they get like less and less dense over distance, so it would fade away like a gradient. It wouldn't be a hard line like this. So red supergiants would absolutely not look the way that we see them in the media. Sam is interested on how elements are formed and end up on planets. That's a very big area of astronomy, astrochemistry actually. and definitely not my area of expertise, but supernovae and red supergiants are responsible for a lot of dust. I think red supergiants make most of the dust in the Milky Way, or have made most of the dust in the Milky Way, and then extra stuff happens when they're around stars and they congregate and all of that stuff. So thanks for all of your questions. Thanks for your patience. Thanks to Lycos and everyone, Tommy and all of you that stuck around to help me figure out what was working and what wasn't working. This is actually super helpful because I can't do it on my own. And so thank you very much. That made my day. Restream fucking broke my heart, and then you guys really helped. So thanks very much. And I'll see you in the next one, I guess. And hopefully it will work without any issues like this week. I love you guys, and I'll see you next week. Bye.